So for programming, in the concept of programming, whether it can be done with the help of the high-level language or low-level language or machine language, what is more important to write the steps of programming in terms of the algorithm. Now, algorithm can be expressed using the pseudo language, irrespective of the syntax of the any specific language related to the microprocessors. So pseudo language can be used. That is a stepwise the necessary steps what to be done under each step. And alternatively, using the flowchart. So flowchart is an visualizations of the steps for programming. So what are the steps? For example, in a problem, write the software program to obtain the sum of the n natural number. Only 8-bit registers are to be used. So that means 8-bit registers, maybe that means so one register would be named as sum. So sum is equal to sigma I, where I is the ith natural number. From the beginning, that is the first natural number to up to n natural number. So that is the simplest way of the steps for this problem statement. Now, some conditions should be put in the programming. So what should we note down all the constraints? In this problem, since we have to use only 8-bit register, the sum cannot exceed 255. So that is one first big constant. If the summation result of sum becomes less than or 255 or 255 or greater than this, the summation should be stopped. Otherwise, what will happen? Because if we are using the 8-bit register, so the 8-bit register can store the maximum decimal number 255D. So it will be overflown to 0, the result. So that is the limitations of the summation using the 8-bit register. But if we use a 16-bit register, then the result can exceed, the result of summation can exceed 255. And according to the maximum number which could be stored in a 16-bit register will be 65,536. So that is a constant. So that means these are the constant. So constant should be also in terms of the steps, written in terms of the steps. That means using the division, that means if sum greater than or is equal to 255, it will stop. So this is the flow diagram or flow chart. How this constant can be incorporated in this division box. This is called the division box of the flowchart. That means the division box has one directed arrow as an input and the two directed arrow coming from the conditions, either true condition or the false condition. So if the sum is less than 255, the addition will be repeated. That means using the generate next number. So that is one way how to write the flowchart for the program or algorithm. So this is one flowchart related to the Fortran programming, Fortran statement. So that's why it is called the Fortran flowchart. Otherwise, in case of a microprocessor language like 8085, this can also be expressed in terms of the assembly statement. That is also possible. So this is one alternative way to how to write the assembly statement in terms of the necessary registers. So the result of summation or the sum variable that corresponds to the accumulator or A registers, which must be initialized to 0 at the beginning of this flowchart. And how many natural number has to be stored? How many natural number are to be included for summation? So that is given by the n, and that should be stored in another register, C register. Then the summation will proceed. So what is the summation? The summation will require the two operands or the two register variable. So the content of the A register variable is again moved to the B register. So that's why the summation will proceed on these two registers A and B. But it should be incremented by 1, the content of the B registers. Then again, what will happen? We have moved the A register, so this is a duplicating step. Then this is the summation procedure. That means in this step, we can use this assembly code like sum add the content of the A register, one of the accumulator, one of the operand as the accumulator, and the B register should be summed, and the result of summation should be stored to the accumulator. So after each summation, each summation means how many summation will proceed to add the n natural numbers. It will be n minus 1, definitely. So that's why the number of count after additions or after summation of each summation, the register, C register, content of the C register should be decremented at this stage. C is equal to C minus 1. Now here is a conditional flag. Here we are using the 0 flag. If 0 is equal to 1, Z flag is equal to 1. How the Z flag will be set? When the content of the register after decrementation will become 0. So if Z flag is equal to 1 or set means all n number of the natural numbers, n times of the n number of the natural number have been utilized for summation, and the process will terminate at the stop. So this is called the terminator of the flowchart, start and stop. If not, the 0 flag is not set, that means it is reset at 0, summation will be repeated. So there, that means this can be expressed in terms of assembly statement. So that's why the flowchart is very important. That means once the flowchart has been developed, so after visualizing the flowchart, everybody can write the assembly statement or in programming language. So that is the outcome of the flowchart. So this is the assembly statement which has been programmed. This flowchart has been realized or implemented in terms of the assembly statement. Here we are using the symbolic level for branching. Here we'll check the conditional 0 flag. If no 0, that is ZNZ, the summation will be repeated. So the branching will occur at the symbolic level next. Otherwise, the program will terminate at the halt statement. So this is the one simple program in 8085 called the assembly language program for sum of natural numbers. Here it should be kept in mind the count value will be such so that the result of summation which is written at the accumulator should not exceed 255 decimal or FF in hexadecimal. If we suppose the n may be a byte number with this NVI C, n statement, that means it may be maximum 255 value. That means 255 natural numbers could be summed, but it should be kept in mind. That means whether the 255 all natural numbers, the result will exceed the 255 or not. That means the sum should be less than 255. So that is the equation from where the maximum value of the natural numbers could be found out. The value of the n should be less than 2 only 22. But if we set the value of the n greater than 22, then what will happen? The variable sum cannot store the result of summation. It requires variable sum. Why? because it is 8-bit registers, a byte registers. So that's why you have to change the register variable that the accumulator has been used to store the sum. See, A is 1 byte registers. So that's why you have to change the assembly language. What will be the content of the change? That is illustrated here. That means if we want to add the number of natural numbers exceeding 22, so this will be the nature of the flow chart. Where here we have to use the variable which can store the result of 16-bit number, that is HL pair. So HL should be initialized to summation order. That means we have to add the lower order byte followed by the addition on the upper higher order byte. So that is a change. Number of count will be stored to the another pair registers, BC pair. And the result of the summation is now, that is D register pair. So all the 3 pairs have been utilized. And there is the repetitions of some 16-bit addition will proceed. Content of the HL and the D, that is the 16-bit addition number, will be added. So the natural number is retained in the D register pair. What will be the maximum value of the natural number? Definitely it will be 65,536. So range becomes higher. So similar way, we have to check the conditional flag, 0 flag, whether it is 1 or not. That means if the number of count which are where BC content is becomes 0, the 0 flag will be set. So that means we are using the BC register pair decremented, should be decremented by 1. And accordingly, when the content of the BC register pair becomes 0, the 0 flag will be set and the summation process will terminate. Otherwise, it will be repeated. So this flowchart is the ALP of the sum of the n natural number. The value of n is greater than 22. So this is a 16-bit addition, repetitive addition. And these are the assembly language, 8085 assembly language, which can realize this flowchart. So this is the final outcome of this program. So this is a good example. This is the second example. And before that, it was the first example. So you must go through this note. That means how the flowchart can help the programmer to visualize the condition, constraint, everything. Now, another feature of the programming is that repetitive in nature. So, repetitive in nature, that is called the subroutine programming. For that, when the problems in the programs are repetitive in nature, which should be invoked at a different part of the main program in a repetitive manner. So the techniques is to write that part in the form of subroutine. The subroutine is not written inside the mainline program, but somewhere else, outside the scope of the mainline program. And it should be called. That is why the instruction will be like that, call subroutine function. And subroutine will reside not in the sequential manner of the mainline program. So after calling the subroutine, the CPU will automatically branch to that starting locations where the subroutine resides. When the CPU encounters the last instruction of the subroutine, it will come out to the mainline program. So that is the nature of the subroutine. So subroutine by definition is a set of instructions which are used repeatedly in a program can be referred to as a subroutine. Only one copy of this instruction is stored in the memory. That means the subroutine, the assembly code will be set to part of the memory or memory. When a subroutine is required, it can be called many times during the execution of a particular program. That means subroutine will be called many times. There is no restriction. So in doing that, by this technique, subroutine programming, a part of the common part of the program can be repeatedly called, which result the size of the program will be the least. Otherwise, without going through the subroutine, if we write the program in such a manner, so this common part will be again written at the different body of the program. So in an effect, the size of the subroutine code will be added up, which will increase the total size of the program. So it is a very inefficient way to write the program. But using the subroutine program, which is repetitively, it can be repeatedly called within from the main part of the program at any point of the main part of the program in a repetitive manner, so that the total size of the main program or main line program will be the least. So that is the advantage of subroutine programming. Subroutine can be nested. That means from one subroutine, another subroutine can be called. Another subroutine can be called. As many more, that means subroutine can be called. So it can be nested. Now, that's why how the main program will refer to the subroutine. That is the address of the starting address of the subroutine. And it can be branched with the help of call instruction, that is called. So when the call instruction will encounter, what will happen? That should be understood. That is why a part of the memory should be used as a stack memory. Now, what is the purpose of the stack memory? The characteristic of the stack memory is like that. The stack is an area of memory identified by the programmer for temporary storage of information. So this is the that is the memory address map of 8085 of volume 64 kilobyte size. But some part of this memory area of this memory space must be referred to as a stack memory. So stack memory is utilized with the help of stack pointer register. There is a register 16-bit called the stack pointer. The stack pointer registers will retain the bottom of the stack memory address. The bottom of the stack memory address will be set by the programmer or the user. That may be here, that may be the bottom, that is maybe the 0 hex, or maybe leaving some part a particular address which is falling within the address map of the 8085. Now, how the stack memory will be used during programming, that is repetitive nature of the programming with the help of the calling statement. The nature is like that, the stack normally grows backward. The address is written by the stack pointer register. So stack pointer must be initialized, that is the bottom address of like this statement. LXI SP, load the stack pointer with the help of a particular address of 16-bit. F. It may be anywhere, that depends on the user choice. So in the 8085, the stack is defined by setting the stack pointer register. This says the stack pointer the location here. Now what will happen? The size of the stack is limited only by the available memory. That means if we set here, then the whole memory space may be utilized as a stack memory. So that's why the stack memory, at the worst case, the stack size will be equal to the size of the address space of the 8085. The saving information, why the stack pointer? What is the role of the stack pointer? That should be understood. So 8085 provides two instructions. One is called the push, another is called pop. Push and pop are used storing the information onto stack and retrieving it back. Both push and pop works with the register pairs only. For example, if we write push B, a single byte register. So after executing this instruction, what will happen? The content of the BC pair registers will go to the memory location as pointed by the stack pointer. So this is the content of the BC register pair. The C register is holding F3 and B register is holding 1, 2. So this is the last location of the stack pointer. It was. So the content of the B register will go here, and the content of the C register will go to this location F3. And the stack pointer will be automatically decremented by 2. So the up-to-date stack pointer content is like that, triple FC. So that is called the LIFO order, last in first out order. So the content of the BC register pair that has been stored in a stack area or stack memory, and the stack pointer will be updated with the current value of the 16-bit. Now, in case of the pop D, retrieving the instruction from the stack memory, the reverse action will take place. That means the content of the, say, pop D means retrieve the information from FFFD as F3 to E registers and FFFE as 1 to 3 registers. And the stack pointer content will be incremented by 2 so that it becomes here. Because it indicates that, yes, this information has been retrieved to the D registers by the data movement operation, and definitely the stack pointer must indicate here. So that is done by the single byte instruction called pop D. So that is the actions of the push and the pop instruction. We can also use another register pair, push H, pop B, according to the choice. So what is the operation of the stack? During the pushing, the stack operates in a decrement then stored style. The stack pointer is decremented first, then the information is placed on the stack. During popping, the stack operates in a use then increment style. The information is retrieved from the top of the stack, and then pointer is incremented. The SP pointer always points to the top of the stack. This is very important statement for stack operation. So the order of push and pop must be opposite of each other in order to retrieve information back into its original location. So this is called the LIFO, last in first out. Even the content of the flag registers can also be saved to the stack memory by using the instruction push and pop PSW, program status bar. Using the program status bar, the content of the accumulator and the 5-bit flip-flop information that can be stored. That is the flow diagram. That is the flag content is 80 and the content of the accumulator is 12. So if this instruction is executed, that is push PW, PSW, the stack memory will store this information to the flag registers, and the accumulator and the stack pointer will be updated after decrementation by 2. Similarly, in case of a pop register, pop operation, pop PSW, the reverse action will take place and the stack pointer will be incremented by 2. So that is the push and pop instruction. And similar examples, a piece of examples are given. That means how the stack pointer can store the processor status word or program status word. So this information now, how the stack pointer can be utilized, or stack pointer register can be utilized, and the stack memory can be utilized for subroutine calling. So what is subroutine? A subroutine is a group of instructions that will be used repeatedly in a different locations of the main program. That we already discussed. But how the stack memory will help for subroutine processing. So how the subroutine will be called, invoked by call statement, which requires 16-bit operand or 2-byte operand, which indicates some address. The call instruction is used to redirect the program execution to the subroutine. Similarly, the RET instruction, return instruction, is used to return the execution from the calling routine. And this is the pictorial diagram how the call instruction, how the execution of the call instruction will be done. For example, call 4000 X, a 3-byte instruction, because the call instruction requires, it is a branching, but not a conditional or unconditional branching, but it is a calling, it is a branching under special case, that is subroutine calling. It is for the subroutine calling. That's why the call 4000 here. When call instruction is fetched, the microprocessor knows that the next 2 memory location contain the 16-bit subroutine address in the memory. What is that? 4000. So what will be done after execution? The execution will be like that. The content of the temporary register W and Z, that will be copied to the 4000, and the content of the where the call instruction is residing, this is the address of the mainline program, 2000 to 2003. Why 2003? Next available memory location, because the call 4000 instruction will consume the 3 bytes. That will be 2000, 2001, and 2002. So the next available location in the main memory or program memory is 2003. So upon execution of the call 4000, what will be done? The program counter, this is the address. So this address will be stored, will go to the W and the Z registers, all the temporary registers of the 8085. And the program counter, that is the PC, which is the main indexing register for instruction fetching, that will be changed. Where? Next available location in the main memory, that is 2003. So program counter, that is the program counter, that is the, depending on the stack pointer condition. Initially, for example, the stack pointer has been indicating or is indicating this address. So the next available instruction, that will be saved to the stack memory, that is 2003. And the program counter will be automatically branched to the 4000, will be automatically loaded by the 16-bit operand which is assigned to the call statement, that is 4000. So once the program counter will be assigned to the 4000, the CPU will automatically branch to that memory location where the subroutine codes are written. So with the help of the stack memory and special calling, the instruction will be executed under subroutine. But what is the role of these two address 16-bit? That means that in the subroutine also, the last instruction will be returned. So when the return instruction will be executed, the reverse action will be done. So program counter will be loaded to the saved location, the saved content, that is 2003, which is the next available locations in the memory. And the stack pointer will be incremented by 2. Once the program counter during execution of the RET instruction, it will return to the main program to the next available memory locations, that is 2003. So by this way, a subroutine action or the calling of the subroutine will be done with the help of stack memory as well as the program counter. How the program counter will be updated. So the MP reads the subroutine. These are the steps which I have told. MP reads the subroutine address from the next 2 memory locations and stores the higher order 8-bit address in the W and stores the lower order 8-bit address in the Z register. Both are temporary register. Puts the address of the instruction immediately following the call onto the stack, that is the return address. Here, what is the return address? Return address is here, that is 2003. So that must be stored in the stack memory. Loads the program counter with the 16-bit address supplied with the call instruction. That means this address, new address, will be temporarily saved to the temporary registers, 2 temporary registers of 1 byte, W and Z. So after storing the next memory location, available location, the stack pointer, the program counter will take the next instruction from where it will fetch the read the byte from the temporary byte. So the 4000 will be loaded to the 4000 byte will automatically move to the PC content. So that is written in this statement. Loads the program counter, that is third statement. Loads the program counter with the 16-bit address supplied with the call instruction from the WJ registers. In the subroutine, the last instruction will be the return. So what will be the action upon execution of the return instruction, which is single byte? This is the pictorial diagram in stack memory. So the program counter will be loaded automatically, this information which are stored in the stack memory, that is 2003. And the stack pointer will be incremented automatically by 2. And this 2003, this action will be done when this is the last instruction of the subroutine, the last instruction is return. When this will be executed, that means every subroutine must terminate with the return RET statement. So things to be considered in subroutine, the call instruction places the return address and the 2 memory location immediately before where the stack pointer is pointing. You must set the stack pointer correctly before using the call instruction. The return instruction takes the contents of the 2 memory locations at the top of the stack and uses this as the return address. Do not modify the stack pointer in a subroutine. This should be remembered. Very careful. Do not modify the stack pointer in a subroutine. Otherwise, the whole thing will be disturbed. You will lose the return address. So these are the process by which the subroutine and these are the cautions with the push and the pop instruction. You must remember. Similarly, the conditional calling and return instruction RT are used. What are the conditional subroutine calling? CC, CNC. Call if carry, call if no carry, as well as the conditional returns are possible, not RET, RC, return if carry is set, return if no carry, etc. So these are the examples. This is the mainline program. At the start, stack pointer must be initialized by a particular bottom address. Here the subroutine has been called at the address 1420 hex. It will be 2014 in the reverse order because the lower byte will occur first in the operand and the upper byte will be next. So 2014 is the subroutine address. So it will be like that. It will be 2014. This is not C014. It will be 2014. That is the subroutine has been referred by the address level delay. So these are the common body of the subroutine. At the last, it will be a terminating instruction that is returned. So once the subroutine will be fully executed and the CPU will branch to here, because this information C00A has been stored in the stack memory during the execution of the call instruction. Similarly, here the same subroutine has been invoked at another part, and same thing will occur. So that's why you can understand that means the size of the main program is how much? The last address is C0, 1, 2, 1, 2, and 1, 3. So C0, 1, 3 is the last address and the initial address is C00. That means 1, 3 hexadecimal bytes from this part to this part has been utilized for the mainline program. Plus, this is the size of the subroutine. The length of the subroutine is, say, it will be 2020 minus 2014. So it will be a 14 byte hexadecimal. So this plus this will be the total byte. Otherwise, if we do not use the subroutine, we have to write this code here, then the similar like code here. So the total size of the main program without subroutine will be much more than that used in this structure. So that's why the subroutine way of programming will give you the modularity. That means the coding should be done one time. At the same time, it can be invoked without any repetition for any number of times. Now, whether you can understand this concept is not, please. Have you understood this concept of subroutine calling and what is the function of the stack and how the stack memory operation is done with the help of the two instructions, push and pop? Hello. So did you understand the concept of subroutine? Yes or no?
Yes, sir.
Yes, sir.
So stack is nothing but a particular type of operation on the memory space. It is used only for the subroutine calling. Means when the repetitive tasks in a main program will be done, then the subroutine calling is the proper way or proper method. So I'm giving the example, some example of subroutine. This is one such example. The factorial of an 8-bit number. Whenever there is in the problem statement, there is a repetitive nature of the task, like factorial programming. So definitely you have to write this type of program in the form of subroutine. This is a flow chart. 8085, which is the 8085 registers. And this is a normal way of programming or not using subroutine. What is the subroutine? That is multiplication, called mul. What is the absolute address, starting address of the subroutine? Here it is written F010. So the starting address of the program is F1000. At the beginning, the number has been loaded, but it is better to write initialize the stack pointer, which has not been done here. So before that, we must use the statement LXI SP to some stack location address. Otherwise, it is implied that by default the stack pointer has been loaded. It is not like that. User has to define. What is the multiplication? That is This is the multiplication. Last statement of the multiplication. Now, you can understand how repetitive multiplication or repeat multiplication has been invoked by subroutine calling in a repeated manner. What is the logic of the factorial n? Factorial n means n into n minus 1 into n minus 2 up to 1, the last number. So load the numbers, given numbers, which has been stored in the 8000 memory location. That's why memory indirect address has been used. So load the number to the B register by these two statements and set the D register to 1. That is the last number of a factorial. Then what will happen? Multiply subroutine has been invoked. What is the task of the multiplication? It will multiply the number in D register as well as the B register. You check the subroutine. And the result will be stored where? To the D registers. So B and D registers, that will be multiplied. The result will be the first number, and that will be moved to the D registers. Then it will come out from the subroutine. Then what will be done? Decrement the B registers content. Means, according to the factorial, it is n into n minus 1, the true product. So that's why the next number will be n minus 1. How long the decrementation will be done? When the B registers will not be incremented to 0 or decremented to 0. That's why the repeated calling of the multiplication is A and Z fact. Here the looping will go on. So if not 0, it will be not 0. That means Z is equal to 0. It will go on branching. Here is the subroutine calling. When Z becomes 1, that means when the B content of the B will be 0, then the Z becomes 1. Increment the next location, INX, show the result. That means the result of the multiplication will be stored to the next location, which is 8001. Because HL pair is holding this number 8000. So next memory location after implementation of the HL pair register will be 8001. And store the result of the factorial, which is stored in the D register, will go to that location, that is 8001. Then the program will terminate. So that is the one example of how you can use the factorial n, how to find out the factorial n by subroutine calling. Very efficient and the compact programming. Otherwise, if you write without subroutine calling, it will be a large, bigger program. So 8000 for this example, 8001 will retain 78. That is the factorial n. As because the value of the n has been, I think, initialized to some number 5. So 5 is the input number. The factorial 5 is how much? 5 into 4 into 3 into 2. You find out. So that should match to the data stored in the here. Is it okay or not? Check it. Maybe different, I do not know. It is incorrect, but check it. That is 5 factorial. How much it will be? 5 factorial is how much?
120.
120. Is it so? There it is. 120. where it is. So it is incorrect number. No, it is in hexadecimal. Please convert it to
Yes,
decimal.
sir,
Is it okay? I think 16 into 7 plus 8. Is it
yes,
128?
yes.
Yes. So this is okay. So the result is in hexadecimal, not in decimal.
I told you in decimal. Sorry, sir.
Okay. So at apparent to you, that means apparent that means we are considering decimal number. It is not. It is a hexadecimal number, 120. So in that manner, this is an example of the subroutine. Another example, how to generate the Fibonacci, how to find the factorial of a number without. Yes, it is also the same program using the subroutine calling. But here the explanation is written. What will be done at each step. This is the program code. This is the algorithm. X085 algorithm. You must be familiar about how to write this algorithm. Sometimes in a question, it will be asked to write the algorithm. And what is the memory map layout after execution of this program? The data part and the result part. Data is the input data factorial, and result is the factorial 4. So factorial 4 is 4 into 3 into 2. In hexadecimal, it will be 188. That is 16 plus 8, 24. So this is the example. You must be conversant about the factorial. And this is another program for example of the factorial, not factorial subroutine. A set of 10 packed BCD. What is packed BCD number? That you must be conversant about the code conversion program, binary coded decimal. So the value of the maximum binary coded decimal will not exceed 9 because there are 0 to 9, 10 symbols in BCD code. So 10 BCD packed number. A set of BCD packed number. What is the meaning? So these are the BCD packed number. A single byte. That means it is basically decimally 1, 2, 2, 3, 4, 2, not hexadecimal, because the input data are given in the packed BCD number. Why packed? Because each literals in the decimal, in the unit positions and the that means in the 10 positions are packed, and it is expressed in single byte. So 1, 2 is a byte, but in packed BCD. So in packed BCD, what will be the maximum number? 99. The value of the packed BCD number will be 99, which is 2-digit number. So similarly, the 55 is a 2-digit numbers in the packed BCD format. So how to add all these numbers? These are the set of the 2-digit BCD number. So this is the algorithm. Algorithm says a BCD addition, not the normal addition. BCD addition means you add in a similar manner as in the normal binary addition. Then the result of addition must be adjusted with the special operation like decimally adjust instruction. So for each addition, this is the three distinct process. These are two distinct process, and you must check the carry flag. If carry is not, then it will come out. If carry is there, update B and decimal adjust. So this is the logic of BCD addition, and these are written also. And this is the code. This is also the flowchart of the same problem. This is a program in assembly language. This is a program in assembly language. This is the last statement of the assembly language program. And this is a subroutine called BCD add. The last statement of the subroutine will be returned. And there is another subroutine which is called the unpack, which is referred by its level, symbolic level unpacked, which must have the same, that is another. So two subroutine has been utilized. So these are the input data in packed BCD. So what will be the output of this BCD number? That BCD output number will be stored in a memory location. What is the memory location where the result will be stored? Memory location is, I think, 8060. 8000 is the beginning or starting address of the program, and 8040 is the starting address of the input data storing the BCD number, packed BCD number up to 49, and the result will be stored here, 8060. So 8060 is a location and onwards to store the BCD addition. This is another use of the subroutine. But how the BCD program or BCD addition should be processed, that can be explained separately. I'm just sending. I think it will be easier for you. This is a flow chart for BCD addition. And this is the assembly language for adding two BCD. These are the two BCD number 99 and 25 called the packed BCD format. So according to flow chart, A should be loaded with the first operand, that is one BCD number, and A plus next memory element. Then the decimal adjust operation will be done. What is that? Then store the result of the BCD addition to A. And the carry flag should be checked. If it is true, it will be 01A and store it to the memory. Or if it is false, it will end. So that is the structure of the assembly program without subroutine, a simple BCD, where the result will be stored. 8000 is the starting, 8000 is the address locations of the input number. First, 8001 is the second memory location. So where the result will be stored? Result will be stored the destination address 8050 and 8051. So 2-byte consecutive location is the result memory location 8050. And how the addition, after the BCD addition, the addition will be done or adjusted by decimally by this instruction, decimal adjust for addition, DE. Okay. That means what is the role of this addition, DA? What is the role of this DA instruction? Suppose the two BCD number is 66 or two BCD number is 1212. What is the result of decimal? It will be 24. Okay. But if one number is, suppose the two numbers are given as this 9925, what will be the decimal addition? it will be 4 in the unit position. 9 plus 2 is 11. Then it will be 11. So 1, 1, 4 is the result. But whenever the simple addition will result, it will not be like that, because 11 will be in hexadecimal in how much? B. So B4 will be the result, and B4 is not the BCD number. So at this point, that means whenever we add simply the two element, microprocessor cannot know whether the element are in BCD. They will simply consider the numbers in binary. That's why they will add simply in the result of the accumulator will be B4. So when the B4 will be adjusted decimally automatically at this step, the B will be 11. So it will be 3-digit BCD, that is 114. So how the 114 will be accommodated in the single registers, because 2-digit packed BCD is written by the single register. So 14, that is a BCD part that will go to the accumulator, and the carry flag is set to 1. That means from this decimal adjust operation, decimal addition, the result has the two parts. One is called the sum, which is in BCD, which must be explained in BCD, and the carry will be stored to the carry flag. Here the carry will be 1. So that's how you can see if the carry is 1, it will return. That means it will 14 will be saved to the memory location, but carry will be written. And in the program body, you can see, so carry is saved at this statement in the next location. Where the location is 8050 is the storing the result of BCD addition, and now 8051 will be the next location to store the information from carry. So in an effect, the result of this program will be 1, or the 8051 will store the 1, and 8050 will store the 14. So that's why it is a BCD addition. In the previous program, there is an array of the BCD number which can be added, which can be summed with the help of repetitive manner, subroutine calling. So now this is the BCD addition. You must understand that in how to add the two BCD number. Now, did you understand that BCD addition? What is the difference between the normal addition and the BCD addition? BCD addition differs in a normal BCD addition differs. That means every digit literals will be maximum 9, not exceeding 9. And to do that, DA instruction should be used. Decimal adjust after addition. Decimally adjust after addition, DA. So with the help of DA instruction, it can be converted to the BCD again. But the result will be done in previously, the result will be in the normal binary addition. But DA should be used. So that is an important concept for against this BCD addition. Similarly, there are so many problems out there. I have already explained the stack theory, and these are the examples. So you can go for these notes, etc. And this is for subroutine or stack operation in memory. So these are example of the how In 8085, there is no instruction like multiplication, division. So multiplication can be conceived as a repeated addition in 8085 program. So this is the flowchart for how the 8-bit number can be multiplied by a 8-bit another multiplier number. So what is the maximum value of the 8-bit number? 255. What is the maximum value of another 8-bit number? 255. So if we multiply the 255 into 255, it will be how much? 65,535, I think. That cannot be written in the single byte register. So the result of multiplication for a 2-byte number would be a 16-bit number. That you have to keep in mind. And here this program does not consist of this type of constraint. The result is stored in a single location, memory location. What is the memory location? This is the program location. So starting location is 8000, and the result is yes, same 8050. So 8050 is the destination address, which can store the lower order byte of the product. Also, 8051 is the next location which can store the higher order byte of the location, because already I have told you the result of 2-byte number will not be limited to single byte result, but it will be 2 byte. So that's why the result must be expressed in 2 byte. So that's why to store the 2 byte, 2 destination locations are required. One is 8050, another is 8051. So this program is a multiplication of 2-byte number. Based on this concept, we can also write the multiplication of a single byte with a 2-byte number. A slight change will be done here. This is a multiplication program with 2 byte. That is, 1 byte is multiplier, another byte is multiplicand, and the product will be 2 byte. Product will be 2 byte, and the multiplicand and the multiplier will be single byte, 1 byte. There is another program that is a number test, whether odd and even or prime, whether the given number is prime or not. What is the logic to find out this condition, whether the number is prime? A prime number is one which has only 2 divisors, 1 and the number itself. A composite number, on the other hand, has 3 or more divisors, non-prime number. So these are the two things based on which the algorithm should be developed. To go through the algorithm and implement in the form of steps, and this is the program. To find out whether the given number is prime or not. The next program is the odd and even number test. How you can test a given number is odd and even? The number is said to be odd if its lower bit is 1, otherwise even. Lower means that means least significant bit is 1 or not. So that you have to test according to the given algorithm, and these are the program body. Expansion of this program is like that. To find out the square root of a number. Similarly, you can find out the square root of a number. How? The algorithm is like that. Number whose square root we need to find is stored in the memory location 2050 and stored the final result at the location 3050. How the result? How you can extract the square root? These are the explanation. Squaring of a number is easier, but finding the square root is because the concept of the prime number. That means whether the given number is a whole number or not, you have to check. Then you can do the square rooting. For example, you cannot find the square root of that 2, but you can find the square root of the 4. Then after then 4, it will be 9. So whether the we have to prove. For that, the concept of the prime number will be given. So the programming is a very conceptual part. You must be conversant about the programming logic or algorithm. Similar division could be done, but it is a harder. As such, there is no division. Division is what? Multiplication, I have told, a repetitive addition. But in case of a division, what logic should be followed? Multiplication is a repetitive addition task. Say 3 into 2. In case of 8085, to multiply 3 into 2, what you have to do? Either you can add the first operand 3 times or the second operand 2 times. That is the simple logic. But in case of a division, that is 4 divided by 2, what you have to follow? 4 divided by 2, result is 2. What will be the algorithm? What will be the logic behind the division? It will be a repetitive subtraction. So you find out which operand is lesser than the another. You take that operand as an input number. Then you go on subtracting from the another number, that is 8 or 4. So among 4 and 2, 2 is the chosen number. Why? Because 2 is lesser than 4. You cannot choose 4. So then you go for subtraction, repetitive subtraction. From 4 minus 2, it will be 2. Then again subtract 2 from the resultant number 2. 2 minus 2, it will be 0. And go on counting how much subtraction you have performed. It is 2. So the result of division will be 2. In a certain case, for example, in a repetitive subtraction task, the remainder will result. It will not be 0. In that case, the division will not generate the whole number or perfectly divisible number, but you must consider the quotient part as a result of division, and the remainder part is not. Remainder part will left off. That means will unconsidered. So that may arise if the input number is not a whole number or it is not perfectly divisible. But 4 by 2, 4 is a perfect divisible number. But 6 by 2, it is a perfect divisible number. But 7 by 2, 7 is not a perfect divisible. In that case, the resultant or the residual, that means the residual, there will be residual number. How much? 1. 1 will be the residue. You must consider. And the result of division will be 3. So 3 into 2 plus 1, 6 plus 1. So residue will be 1. Or remainder will be 1. So sometimes the remainder may be 0 in case of a perfect divisible number, remainder may be non-zero in case of a non-divisible number. That you must keep in mind. And this is the division logic. These are division flowchart, and these are 8085 assembly language for dividing a single byte number to another single byte number. But here, the input number is 16-bit. So the dividend is 16-bit and the divisor is 8-bit. So 16-bit by 8-bit. Result will be 8-bit, definitely. But you can modify this program for 16-bit, 8-bit number to 8-bit number. 8-bit number, division of 8-bit number to another 8-bit number. You can modify slightly, but the program logic of the program remains same. Here, this is the program. That is, divide the two 8-bit number. This is the program. This is the assembly language program. So the multiplication and the division programs have been explained. You must understand and you can practice by using the simulator. And these are how the DA instruction performed or is performed. That is DAA instruction, decimally adjust for addition, which are required for converting a binary number to BCD number. So how to transfer a block of data byte from source location to the destination location. This is the logic expressed in flowchart, and these are the program. That means, what is the input data? A block of data byte stored in a source location from 8000 to up to 8008, 10 bytes. And this memory block will be shifted or will be moved to the another destination location, 9000. And the last memory location will be 9009 or 9000A. So these are the outcome of the program. Very simple. You study this logic, flow diagram, you can understand what to be done. And this is the assembly language code. So these are the important nature of the program you must practice. This is a Fibonacci number. What is the logic of the Fibonacci number? This is expressed here. You have to input is the logic in the flow diagram. And these are the assembly program. Now the consecutive Fibonacci number you can generate. What is the condition of the Fibonacci number? The current Fibonacci number Fi is equal to Fi minus 1 and the F minus. That means sum of the two previous numbers. For all I greater than 2. Which F1 is equal to 0, F2 is equal to 1. So the F3 is equal, F3 will be 3, F3 will be 1. And F4 will be 2, like that. So these are the Fibonacci series. And this is the generation of Fibonacci number. Okay. So do you know the Fibonacci number? And so many numbers are there which are very important. This is an arithmetic, simple arithmetic program nature. Then one of the important program is sorting and searching. What is meant by sorting and searching? That is arrangement of the number in descending or ascending order. This is called the sorting. And searching means to find out a particular element of an array of a digits if it is matched. Otherwise not. It will produce the zero. Write a program to sort given 10 numbers from the memory location 2200 in the ascending order. That means from 2200 10 numbers are stored, not in the unsorted manner, but you have to sort it. What is the logic of sorting? This is the logic of sorting. And these are the program. You can see this is unsorted. The input array, input numbers are stored in the 8000 to 8006 and so on. The order of the number to the respective memory location is not in increasing order. But you have to arrange, after sorting this number, array of the number, in such a manner, the least number will come first, then the next number likewise, and the last element will consist of the maximum number. So that is the sorting logic in ascending order. The descending order is also possible. That is the first element location, the first element will be the highest number of the given array, and the last element will be the lowest number. Again, the condition will be aggravated if there are similar number or repetitive number, say 2, 2, 2, 2. Then in that case, there is no order. That means 2, 2, 2, 2, there is no higher or lesser. So it will come, it will go on consecutive manner. No problem. So here the condition is like that the input numbers are unique in nature, but it may not be for sorting. That means arranging this number in ascending or the descending order. So this is the code. This is the flow logic. This is the code. Ascending order. This is the program code. This is the program code also given in a detailed manner. This is descending order, flow chart, and this is a program statement. Assembly order, this is the program statement. Program statement. Assembly code. Okay. So these are the important assembly language programs which are very, very important for examination purpose, or that means in basic concept also, in clearing your basic concept. Hello? চলছে কেন? পরে হয়। ঠিক আছে। আচ্ছা আচ্ছা। Okay. So did you understand the programming logic and how to write the program? Hello? Did you understand the programming logic, the concept of algorithm and the flowchart? If not, then please tell me in which part you are not, it is not conversant. Hello?
Okay, it's okay.
So today I should end, okay? It will be uploaded, my class note.